In today's video, we are still proving what? The second fundamental theorem of calculus. Proving the second fundamental theorem of calculus. But in today's video, we are not going to be using first principle. We are not going to be using derivative from first principle. What does the second fundamental theorem say? I'm going to state it in another way and then prove it. If f of x is a bounded and integrable function, if f of x is a bounded and integrable function defined on the closed and bounded interval AB, closed and bounded interval AB, and a function capital F of x is defined such that capital F of x is equal to the integral of f of t dt from a to x. Then our capital F of x is continuous on AB, the closed interval AB, and also capital F of x is differentiable on AB with the differential of capital F of x to be equal to f of x for all x elements of AB. What are our assumptions in this theorem? In this theorem, our assumptions are that f of x is bounded and integrable on the closed interval AB. The first assumption, f and integrable on closed interval AB. What's the second assumption? The second assumption is that a new function, capital F of x, capital F of x, capital F of x is defined such that what? Capital F of x equals the integral of f of t dt over the interval a to x. These are our assumptions. What do we want to prove? We have two functions we want to prove. It says then we want to prove that what? Our capital F of x is continuous on AB we will also prove that capital F of x is differentiable on AB with the differential of capital F of x to be equal to f of x for all x elements of AB. So let's write that down. For all x elements of AB. So we begin with the proof. The first is to prove that f of x, capital F of x, is continuous on AB. Remember, we are proving the second fundamental theorem of calculus. We are proving the second fundamental theorem of calculus. And we want to prove that capital F of x is continuous on AB. Prove that f of x is continuous on closed interval AB. Consider x and c, elements of the closed interval AB. Since from our assumption that f of x is bounded, it implies that f of x is less than n for some number n. And this also implies that our f of t will also be less than capital N. By the properties of Riemann integral, then we have f of c minus f of x to be equal to what? The integral of f of t dt minus the integral of f of t dt from a to x. And again, using the properties of Riemann integral again, the integral of f of t dt from a to c minus the integral of f of t dt from x to a. We have made use of that property of Riemann integral to change this to this. If you need to see that, go ahead and look at the video on the properties of Riemann integral. And so our f of c minus f of x is equal to what? The integral of f of t dt from a to c plus the integral of f of t dt from x to a. Still making use of the properties of Riemann integral, our f of c minus f of x becomes what? By the properties of the Riemann integral, this becomes the integral of f of t dt from x to c. From x to c. And the absolute value of this is less than or equal to the integral of f of t dt from x to c, and this is less than or equal to the integral of capital N. Remember, we have said that because f of x is bounded, then it is less than some capital M there. It is less than capital M dt from x to c, and that is less than or equal to n into what? C minus x, assuming our c is greater than x. Now, by the time we take limits of both sides, taking limits as x tends to c, we have limits as x tends to c of capital F of x minus capital F of c to be equals to limits as x tends to c of capital M into c minus x, and this is equal to 0. Therefore, f of c minus f of x is equal to 0, and this implies that the new function capital F of x is continuous at x equal to c, but x and c are elements in the closed interval AB. Therefore, our function capital F of x is continuous on the closed interval AB. Remember that we said we are given the assumptions that f of x is bounded and integrable, and then a new function capital F of x is defined such that capital F of x equals to the integral of f of t dt from a to x. If those assumptions are true, then we have been able to prove that our capital F of x is continuous on AB. We will also prove the second part of the theorem, that our capital F of x is differentiable. We will also prove that our capital F of x is differentiable on the open interval AB with the differential of capital F of x to be equals to f of x. We want to prove that also. Let's look at the proof. Let's look at the proof for that. Let x, element of the interval AB, and also consider the number h such that x plus h is also contained in the interval AB. If f of h, if x plus h is contained in the interval AB, then the differential of capital F of x Using first principle, let's look at it. It gives us f of x plus h minus f of x over h. And this is what? 1 over h into f of x plus h minus f of x. But our f of x, as we were given in the theorem, is the integral of f of t dt from a to x, which also implies that our f of x plus h will be what? The integral of f of t dt from a to x plus h. Therefore, the differential of capital F of x is equal to 1 over h into 1 over h into what? Into the integral from a to x plus h of f of t dt minus the integral of f of t dt from a to x. Now again, by the time we use the properties of Riemann integral, I'm going to skip some steps there. By the properties of Riemann integral, our differential of capital F of x will be equal to 1 over h into the integral from x to x plus h of f of t dt. You can go and look at the video on properties of Riemann integral and see how this translates from here to here. From there, remember we are told that our f is bounded. That was one of the assumptions that the theorem provided. That our small f of x is bounded. And if f of x is bounded, since f of x is bounded, it implies that it has a lower bound m, which is the infimum of f of t, where t is contained in the bound x plus h, in the closed interval x plus h, and also it has an upper bound capital M, which is a supremum of f of t, where t is element of x plus h. Therefore, it implies that our small m is less than or equal to f of t less than or equal to capital M. Remember that our assumption also says that f of x is integrable. The assumption also says f of x is integrable. So integrating over the interval x plus h, integrating over the interval x of h, we have the integral of m dt from x to x plus h to be less than or equal to the integral of f of t dt from x to x plus h, and that is also less than or equal to the integral of capital M dt from x to x plus h. Dividing through by h, 1 over h into the integral of small m dt from x to x plus h is less than or equal to 1 over h into the integral of f of t dt from x to x plus h, and this is less than or equal to the integral 1 over h into the integral of capital M dt also from x to x plus h. I can see that this is beginning to look like that. And since that is looking like that, then small m, by the time we integrate that, will be equal to f of, since f is continuous at x. Now taking limit as h tends to 0, taking limit as h tends to 0 now, our differential of f of x, differential of the capital F of x, will now be what? The limit as h tends to 0, where we start from, capital F of x plus h minus f of x over h, and that is what? That is equal to f of x. Therefore, the differential of capital F of x is equal to d dx of the integral of f of t dt from a to x, and that is equal to f of x. That tells us that the differential of capital F of x is equal to f of x. Proved. We have been able to prove the second fundamental theorem